Before embarking on this fascinating journey through the history of the atom, prepare to test your knowledge. How much do you really know about the building blocks of our universe? From the ancient Greeks to the pioneers of quantum mechanics, the quest to understand the atom has been a long and winding road filled with brilliant minds, groundbreaking experiments, and revolutionary discoveries.
This essay will take you on a chronological adventure, starting with the earliest philosophical musings and culminating in the mind-bending world of modern atomic theory. Get ready to explore the atom's secrets, and by the end, see how well you fare in a challenging atomic quiz. Think you know the difference between a proton and a neutron? Are you familiar with the groundbreaking experiments that reshaped our understanding of matter?
From Democritus to Schrödinger, the story of the atom is a tapestry woven with brilliant insights and persistent questioning. Prepare to be amazed by the ingenuity and dedication of those who sought to unravel the mysteries of the universe at its most fundamental level.
This journey will illuminate the scientific process itself, showcasing how theories are formed, challenged, and refined in the pursuit of knowledge. So, buckle up and prepare to dive into the captivating history of the atom. We'll explore the key milestones, the scientific giants who shaped our understanding, and the surprising twists and turns along the way.
Be prepared to have your preconceptions challenged and your mind expanded as we explore the very essence of matter. The journey begins now, and it promises to be an enlightening one, filled with intriguing concepts and captivating stories of scientific discovery. Are you ready to unlock the secrets of the atom and discover the fascinating story of how we came to understand the building blocks of reality?
From ancient philosophical musings to cutting-edge scientific breakthroughs, this exploration will take you on a thrilling ride through the history of atomic theory. Along the way, we'll meet the brilliant minds who dared to question the nature of matter, and we'll witness the experiments that revolutionized our understanding of the universe.
Our journey begins in ancient Greece around 400 BC with the philosopher Democritus. He proposed the radical idea that all matter was composed of tiny, indivisible particles called atomos, meaning uncuttable.
Democritus envisioned these atomos as solid, eternal, and unchanging, differing only in shape, size, and arrangement. Imagine the audacity of such a concept in a time when the scientific method was still centuries away.
Democritus's ideas, though insightful, were largely philosophical and lacked experimental evidence. While Democritus's theory was a remarkable leap of intuition, it lacked the empirical foundation to gain widespread acceptance.
The dominant philosophical schools of thought, championed by figures like Aristotle, favored the concept of continuous matter composed of four fundamental elements: earth, air, fire, and water. These elements, it was believed, could be endlessly subdivided, unlike Democritus's indivisible atomos.
As a result, Democritus's atomic theory remained largely overshadowed for over 2 millennia. Despite the lack of experimental validation, Democritus's ideas planted a seed that would eventually blossom into the foundation of modern atomic theory.
His concept of an indivisible unit of matter laid the groundwork for future scientists to explore the nature of the universe at its most fundamental level. The very notion of a discrete, fundamental particle challenged the prevailing wisdom and paved the way for a new era of scientific inquiry.
It's important to remember that Democritus's theory was primarily a philosophical construct, a product of reason and deduction rather than empirical observation. However, the power of his idea lay in its simplicity and elegance, offering a compelling explanation for the diversity of matter in the world around us.
The atomos, he argued, combined in various ways to create the different substances we observe, a concept that resonates even with our modern understanding of atomic structure.
Fast forward to the early 19th century, when John Dalton, an English chemist and physicist, resurrected the atomic concept and placed it on a firm scientific footing.
In 1803, Dalton formulated his atomic theory, which proposed that elements are composed of tiny, indivisible particles called atoms. He further postulated that all atoms of a given element are identical in mass and properties, while atoms of different elements have different masses and properties.
Dalton's theory marked a pivotal moment in the history of science, transforming the ancient philosophical notion of the atom into a quantifiable scientific concept. Dalton's work was based on careful observations and meticulous experimentation, a stark contrast to the purely philosophical approach of Democritus.
By studying the behavior of gases and the way elements combine in chemical reactions, Dalton was able to deduce the existence of atoms and their fundamental properties. He proposed that chemical reactions involve the rearrangement of atoms, not their creation or destruction, a principle now known as the law of conservation of mass.
Dalton's atomic theory provided a framework for understanding the laws of chemical combination and laid the groundwork for modern chemistry. he introduced the concept of atomic weight, assigning a relative weight to the atoms of different elements. This allowed chemists to predict the proportions in which elements would combine to form compounds, a crucial step in the development of quantitative chemistry.
Dalton's work was not without its limitations. He believed that atoms were indivisible, a view that would later be challenged by the discovery of subatomic particles. However, his contributions were monumental, establishing the atom as a central concept in chemistry and paving the way for future discoveries that would refine and expand our understanding of atomic structure.
His work marked the beginning of the modern atomic era. Section 4. Thomson's electron, a crack in the foundation. In 1897, J.J. Thomson, an English physicist, made a groundbreaking discovery that shattered Dalton's view of the atom as an indivisible entity.
Through his experiments with cathode rays, Thomson identified the electron, the first subatomic particle to be discovered. He demonstrated that these negatively charged particles were much smaller than the atom itself, suggesting that the atom was in fact divisible.
This discovery revolutionized our understanding of atomic structure and opened up a new realm of subatomic exploration. Thomson proposed the plum pudding model of the atom, envisioning the atom as a positively charged sphere embedded with negatively charged electrons, like plums in a pudding.
This model attempted to reconcile the overall neutrality of the atom with the presence of negatively charged electrons. While ultimately incorrect, the plum pudding model represented an important step towards a more accurate representation of atomic structure.
It acknowledged the existence of subatomic particles and attempted to incorporate them into a coherent model. Thomson's discovery of the electron not only challenged the prevailing atomic model, but also laid the foundation for the development of electronics.
The electron's ability to flow through materials opened up possibilities for controlling and manipulating electrical currents, leading to the invention of electronic devices that have transformed our world. From simple light bulbs to complex computers, the electron plays a central role in the technologies that shape modern society.
The identification of the electron marked a turning point in the history of atomic theory. It forced scientists to abandon the notion of the atom as a simple, indivisible sphere and to grapple with the complexity of its internal structure.
The discovery also highlighted the power of experimental investigation, demonstrating that carefully designed experiments could reveal the hidden secrets of the universe at the subatomic level.
Thomson's work ushered in a new era of atomic research, setting the stage for further discoveries that would ultimately unravel the complexities of the atom. Section 5. Rutherford's gold foil experiment, a nuclear surprise. Just a few years later, in 1911, Ernest Rutherford, a New Zealand-born physicist, conducted his famous gold foil experiment, which dramatically altered our understanding of the atom's internal architecture.
Rutherford and his team bombarded a thin gold foil with alpha particles, expecting them to pass straight through based on the plum pudding model. However, to their astonishment, some of the alpha particles were deflected at large angles, and a few even bounced straight back.
This unexpected result led Rutherford to propose a revolutionary new model of the atom. He concluded that the atom must contain a dense, positively charged nucleus at its center, surrounded by a vast, mostly empty space where the electrons reside.
The deflection of alpha particles could only be explained by the presence of a concentrated positive charge, which Rutherford termed the nucleus. This discovery marked a paradigm shift in our understanding of atomic structure.
Rutherford's nuclear model provided a more accurate picture of the atom, explaining the results of his gold foil experiment and laying the foundation for future developments in atomic theory. The concept of a dense nucleus surrounded by orbiting electrons became the cornerstone of our understanding of atomic structure, replacing Thomson's plum pudding model.
This new model allowed scientists to explain the behavior of atoms in various physical and chemical phenomena. The gold foil experiment was a testament to the power of scientific inquiry.
By carefully observing and interpreting experimental results, Rutherford was able to deduce the existence of the atomic nucleus, a discovery that revolutionized our understanding of matter. His findings paved the way for further explorations into the nature of the nucleus and the forces that govern its behavior.
The nuclear model provided a framework for understanding radioactivity and nuclear reactions, opening up new avenues of research in nuclear physics.